Good morning, everyone. Today we look at graphs in physics. Now, when we look at the universe around us, we want to understand why things are happening and we want to predict what's going to happen if we change something. And to do that, we identify different variables, things like acceleration and force, and then we examine the relationships between the variables. To do that, we're going to do experiments. Now, when you do an experiment, you are going to change something and see what is the effect. Now, the thing that is changed is called the independent variable, and the one that we measure is the dependent variable. And now the most important thing is the results can only be valid if all the other variables except that independent and dependent are kept constant so that they don't influence the final result. A typical experiment would be to take a specific trolley with a mass and to apply different net forces to that trolley and to measure the acceleration that we have afterwards. Now here, the mass of that trolley is my constant variable. The F net that I'm changing is the independent variable, and acceleration that I'm measuring, that is my dependent variable. Our data will be in the form of a table. Then we apply a specific net force, say for instance 2 newtons, and we measure the acceleration, say for instance 1 meters per second square. Then we change the net force, and once again we measure the acceleration, and we change the net force, and once again we measure that acceleration. And then we use that data to draw a graph. When we draw the graph, we draw the independent variable that we're changing on the x-axis and the dependent variable that we're measuring on the y-axis. And when you draw the graph, you end up with a straight line through the origin. Now, a straight line through the origin is immediately going to tell you that here we have the acceleration directly proportional to that net force. In a second experiment, we can change the mass of the trolley, use different trolleys with different masses, and keep my F net as my constant variable. And then my independent variable will still be A. And if you do that, you get a hyperbola as your graph, and that will tell you that A is inversely proportional to mass. And when we combine them, that will give us the equation F net is equal to m times A, which is a representation of Newton's second law. So the shape of the graph is always going to show us the relationship between the variables. If we have, for instance, a straight line here, that is going to tell us they're directly proportional. And directly proportional means if the one increases, then the other increases with that same factor. Say, for instance, we had this x and y. If the x value increases with a factor 2, then for that line, the y value will also increase with a factor 2. We go from the graph to the relationship, but you can also go back. We can use an equation to determine what was the shape of the graph. Now, in this example, they tell us to draw a graph of the power P dissipated in a resistor versus the current I through the resistor. Now, it's always Y versus X-axis. So I need the power on the Y-axis, I need the current on the X-axis. The X-axis is always my independent variable. Y-axis always my dependent variable. So there I have my two dependent and independent variables. And now we need to look at an equation that's got both of them in there to give me the relationship. Now on your information sheets, there are two different equations, both having P and I in there. And now I need to decide which one. What's important is all the other variables must be constant. So I'm not going to use P equals I times V because I don't know what's happening to V. I do know I'm working with a specific resistor, and that is going to tell me that R is a constant. And the moment that R is a constant and I look at that equation with R constant, it will tell me that P is directly proportional to I squared. And we will soon learn that I squared will give you a parabola. So here we have a parabola because the relationship between P and I is P is directly proportional to I squared. So it's very important that we know the different shapes. So let's look at them. First, there, straight line through the origin. That will be when things are directly proportional. If you have the net force on an object versus acceleration, net force versus acceleration, we need an equation, and that will be F net equals m times a. It's got both the net force and the acceleration, and now we've got that m in there. But when they tell you they've got an object, they are telling you m is a constant. And then F net is directly proportional to a, and immediately that will be a straight line through the origin. Next, we look at inversely proportional, and that will be a hyperbola. I know all of you have seen that before. When they give us an example here, they ask us mass versus acceleration. So we need mass on the y-axis and acceleration on the x-axis. They tell you they experience the same net force, and that is going to tell you that F net is now my constant variable. And when I have F net as my constant variable, then M and A is inversely proportional. To give me the same F net on the left-hand side, if M on the right-hand side increases with a factor 2, then A must decrease with a factor 2. If M doubles, then A must halve in order to give me the same F net as before. So they are inversely proportional, and we draw a hyperbola as the shape for the relationship between M and A. But we may choose to put 1 over A on that axis. If we put the 1 over A on the axis, then M is directly proportional to that axis, and then we get a straight line through the origin. In the next one, we look at directly proportional to x squared, and this is where we find the parabola. Now here the example is the power dissipated, so we're looking for P by a resistor versus the potential difference. So we need P and V, and since they tell you they're working with a resistor, then R is going to be my constant. So I can look at that equation with R constant, and that will tell me P is directly proportional to V squared, and that gives me a parabola. Or if I choose to work with V squared as my axis, then that will be just a straight line because P is directly proportional to that V squared. The next one is more difficult, and that one is where we've got something that is constant or not dependent on the other variable. Let's look at the example. The gravitational acceleration of an object, that's G, near the surface of the Earth versus the mass of the object. So we're looking at G and M. You should know that the gravitational acceleration does not depend on the mass of that object. A big elephant and a small mouse will be falling to the ground with the same gravitational acceleration of 9,8 meters per second square if they're near the surface of the Earth. G will have the same constant value for all the different masses. Now the last one is here that you don't see often, and that is when it's inversely proportional to the square of x. We have two examples. The one is Newton's universal gravitational law, where we see that, and you also have Coulomb's law, where we have F equals kq over r squared. We're going to draw a graph of the force of attraction versus the distance between their centers. So we're looking at F and we're looking at R. Now G, M, and M are constant, and therefore F is inversely proportional to R squared. So here we have a different graph. We already know 1 over R is going to give you a hyperbola. That's the black one over there. And now 1 over R squared is going to give you a graph that looks a lot like that one. It's just a little bit different. And it's nice to know what it looks like, but they haven't asked this yet because it is quite difficult. Now let's look at a few questions. 1.1. Which of the following graphs is the best representation of the relationship of the energy? So they're talking about energy, and that's going to be W, needed to move 1 coulomb of charge, so Q is going to be constant. So it's the relationship of the energy needed to move 1 coulomb of charge between 2 points in the circuit and the potential difference between the points. So we're looking at an equation with W for our energy and V for our potential difference, and there can be a Q because we know Q is constant, and for that we have an equation V equals W over Q. That's for our definition of potential difference. We had V equal W over Q, and now that Q down there is a constant, and that's going to show you that V is directly proportional to energy. And for directly proportional, we need a straight line through the origin, and that's why the answer is A. Right, in question 1.2, they ask us which one of the graphs below represents the correct relationship between the frictional force on objects and their masses. So I'm definitely looking at frictional force. Now for frictional force, we have Fk equals mu k times n. Now if I assume there's only horizontal forces, the normal force is going to be equal to the gravitational force. And that is going to be mass times gravitational acceleration. So we end up with our frictional force being equal to mu k times m times g, and from that it is easy to see that the relationship between that frictional force and the mass is they are directly proportional to each other. Because mu k is constant, because they didn't change the surface, and g is constant, we're assuming we're still on Earth. And then the answer is a straight line through the origin for the directly proportional relationship.